So here's a Denavit Hartenberg question from 2019, that's last year. So we're asked to analyse a 4-link planar arm using Denavit Hartenberg parameters. It's actually referring to using classical in this case. We did set it up originally with this question with modified, but now we've obviously moved over to standard. So let's first of all consider the arm. We see that it's got 4 linkages of length L1, L2, L3, L4 respectively, and these are at angles of theta 1, theta 2, theta 3, theta 4 respectively. We notice also that we have Denavit Hartenberg frames associated at least with the first 4. We could also do with one at the end if we want to get the last length as well, and we do. The important thing to notice is that the z-axis, if there was one, which is it would be sticking out of the page, but it's not actually drawn on there, but it would be lining up with the actual axis of rotation as is required. And we also see, when we account for the angle, that basically the x of the previous of the next frame also goes through the z-axis as well, right? So those are necessary things to do for the Denavit Hartenberg condition to be valid. So we're now going to analyse this and also account for the link at the end as well, right? So first thing we notice is, because all of the z-axes are pointing in the same direction, we don't have to align any of them with the alpha. So alpha is always 0, right? All the way through, the alpha is 0. We've got no twist in this arm. The second thing we notice is the fact that this is actually a planar arm means we're not shifting between adjacent joints. We're not going up and down the z-axis. It's not moving further and further up or down each time we actually move along. It's actually staying in the same plane. So that means that D is always 0. And then we're going to have basically the distance between adjacent z-axis is going to be A, and the angle to align the x directions is going to be by theta, right? So theta is the angle theta. L1 to L4 is going to be the corresponding A1 to A4. So we can build up our table, which is of the same general form for all of the linkages. So the first link has theta equal theta 1 and A equals L1. Similar thing for the second one. This time is theta 2, L2. Third one, theta 3, L3. Fourth one, theta 4, L4. Okay, so that's good. So now we know that we can write this in terms of a homogeneous matrix, which will map from the axis to the previous one, and it's of this form. You could either work it out from first principles, or often you'll be given this in the data sheets at the back of the exam questions. So we know that we've got this matrix which relates the thetas, the alphas, the A's and the D's. So the homogeneous transformation that realises the mapping from the endpoint back to the previous joint. In our particular case, because alpha is 0, we can put in cosine alpha as 1, sine alpha as 0, which simplifies it. All the cosine terms just basically go to 1, and the sine terms in alpha go to 0, so they basically reduce the values of things they're multiplied with or are on their road to 0. So it simplifies the matrix. What we need to do then is for each link, we need to evaluate this homogeneous transformation. So for the first link, we'll put in the values with theta 1, L1, second one for theta 2, L2, and so on, until we do that for all of them. So they're all of the same form, except we have the respective theta 1, L1, theta 2, L2, theta 3, L3, theta 4, L4 values for the corresponding transformations for those corresponding linkages. Then what we want to do is evaluate all of these for link lengths of 1 and link angles of 0. So again, that simplifies things a bit. So now we've got the fact that theta is 0, A is 1, that means sine theta is 0, cosine theta is 1. This leads to a nice simple result then for all these values, that we have this simple matrix. As you can see here, we end up with the identity matrix for the part of the matrix representing rotation, and we have a shift along x, right? So that kind of makes sense, because if we actually look at the shape of the arm, it basically means it's not rotating at all off the default base position, and it's just going to represent a translation along x of a value of unity, right? So that's what that's telling us. So that should immediately tell us the answer then. What is the overall transformation matrix? Well, we get that by multiplying them in the right sequence, starting at the end all the way back. So transformation from 4 to 3 times 3 to 2 times 2 to 1 times 1 to 2, 1 to 0. We just have to multiply the matrices out, and unsurprisingly, we end up with a nice simple result. No rotation component in the 3 by 3 part here, and we get a shift of 4 in x. And if you actually look at what this would, this obviously makes a lot of sense. If theta was always 0, we just have this thing lying down on the x-axis and translating from where we start the base here all the way out to the endpoint by 1, 2, 3, 4 units, and that's why we get that result.